Hello everyone. Today we are going to talk about the chapter 13, Life in the Universe. So the ultimate question we want to ask and look for answer is, are we alone in the universe? So you can see in this image, we call it a roadmap for discovering life in the universe. And you can see definitely will start with looking for the origin, evolution, and property of life on the surface of Earth, which will helping us searching for evidence of life beyond our planet. Then next, you can see Mars. If you still remember, we already learned Mars' climate is much warmer and they used to have a lot of water on Mars billions of years ago. They may have helped life begin there. And if we further out in the outer solar system, we have Jupiter's icy moon Europa. And the study showed that beneath the shell of solid ice of Europa, there may lie vast ocean of liquid water that could support biology. And definitely we also have future mission sent to Europa to find out more information about this underneath the surface ocean. And beyond our own solar system, there are stars over there, and they can host their own planet, some of which might be similar to Earth in the ability to support liquid water, as a result, support for the life. So now we are basically pushing actively in all these directions to try to find the answer to the question, are we alone in the universe? Now, let's first take a look at the cosmic context for life. Let's start with the life on Earth. And we know on the Earth, life are built upon carbon-based, or sometimes we call organic molecules. Some basic building blocks of life are amino acid and nucleic acid. They are all organic molecules. So where is those organic molecules come from? Of course, they can be generated or created by some chemical reaction happen right on the surface of Earth. And also, we suspect that some like debris left in the universe can bring to us some organic rich molecule material, such as the comets. And there's even, we think that most of the water in our ocean actually are coming from comets. And our study about the nucleus of comets actually found a lot of organic molecule or carbon-based molecule that could be the material and involving in the later on chemical reaction and build up those organic molecule. Then if we broke down even further to look at the this organic molecule, what kind of element actually used for those organic molecule. And we found that most common element, of course, is carbon. And if you look at this periodical table, you will see that in nucleic acid and amino acid, we also have hydrogen, oxygen, and nitrogen. Those are common elements. And where those heavier elements actually come from? Those heavy elements actually produced by the previous generation of stars. So here, in briefly, what happens is that at the core of the star, the nuclear reaction, the nuclear fusion, basically can fuse a small element and to combine them together to generate a heavier element. For example, like 4 hydrogen atoms will fuse together to form helium nucleus, and 3 helium nucleus will be fused together to form a carbon, and so on and so forth. So therefore, all the elements, if you look at this periodic table, other than basically hydrogen, helium, and a few lighter elements, and all the other elements actually are generated inside the either small stars or larger stars, or during the process of a supernova. If you focus on those elements or atoms, especially important for life, carbon, nitrogen, and oxygen, that's all formed or created through the nuclear fusion at the core of the star. And of course, if those elements are still at the core of the star, there's no way we can use them. However, even though stars living very, very long time, but they will ultimately run out of fuel and they will die. After the death of the star, especially some more violent deaths like an explosion, the explosion will basically give away the heavier element produced inside the core of the star into the interstellar media, like into the space, into the universe, and which will actually incorporate in later generation of the formation of the stars, such as the formation of the solar system. So therefore, of course, since the Earth is one member of the solar system, those heavier elements incorporated into the solar nebula will be later on be used by the formation of the Earth and become a part of Earth and become a part of organic molecule and become a part of life. And if you take a look at those atoms from our own perspective, think about those atoms in your body for a minute. They're not like forever belong to you. You are just kind of borrowing those atoms from the environment of the earth. The atoms actually circulate through our body and live it. For example, with every breath in, we inhale oxygen and exhale the carbon dioxide. And of course, the food we eat and we take into the new atom, get rid of the waste from our body by excrete. So we basically return those atoms in the environment of the earth. Even some atoms actually may take up more permanent residence in our body, will not be part of you much longer than you are alive. Ultimately, we basically will return all the atom in our body to the vast reservoir of the earth. Of course, these atoms will later on incorporate into the other structures, even other living things in the future. If you think about even further away after the death of the sun, the earth is no longer exist. Those atoms will be get back into the interstellar environment and later on will be incorporated again in the formation of the next generation of the star and the planet, and maybe later on be incorporated into a body of a new generation of life. And why astronomers or scientists actively searching for the life? Even if so far there is no solid evidence we actually have life beyond the Earth. It is because when we look at our location in the universe, especially the Earth's location, you can see Earth is not the center of solar system. The sun is not the center of Milky Way galaxy. So there is nothing special about our place in the universe, which leads into that if life could develop on Earth, it should be able to develop in other places as well. Sometimes we call it the Copernican principle. And let's think about it. Even within the galaxy, our own Milky Way galaxy, there are billions of stars. And a lot of them are old enough, so they already last for billions of years for life to have developed on a planet around them. And there are actually billions of other galaxies as well in the universe. So that means by chance, even the chance is very small, it will be on somewhere in the universe, there will be life. And maybe even intelligent life like us in the universe might be also very common. Of course, when we mean intelligent life, that means similar as Earth, they are able to make progress through the application of technology. Because there's a lot of stars much older than the sun, organic life around other stars may already have started a billion years earlier than we did on the Earth. They may have had a lot more time to develop advanced technology, such as send information, spacecrafts, or probes, or even lives between stars. We just have no idea about that at this moment. We might be just a very immature life, intelligent life in the universe. And then the question will be raised. If there's a more intelligent life in the universe and more advanced in technology than Earth, if life is common, why those more advanced life forms have not contacted us? So sometimes we call it the Fermi paradox. There can be a couple of possible answers for this question. Perhaps maybe the life is common, but intelligent life is not that common. The network of communication between the intelligent life will come about in near future, but not yet have time to develop. So far, although human civilization is only very, very short amount of time in the history of the Earth. And if you look at the time for the advanced technology, and it is also a very small fraction of human civilization. And also maybe there are invisible string of data flowing past us all the time that we are not able to detect it because we are not advanced enough or sensitive enough to detect them. Maybe there's advanced species, they already discovered the Earth, but they are not want to interfere with the immature or developing conscious such our own. So they want to let us grow by ourselves without interfere with our civilization. And maybe we do have a civilization that reach a certain level of technology and then could do the travel between stars, but then they self-destructed. That means they no longer exist in our universe or in our galaxy. So therefore, those are all the possibilities, but we still are actively looking for if there are any messages sent to us to actually show that there is other intelligent life exists in the universe. I want to share with you a video about Fermi paradox. Where are all the aliens? And I'm going to only share a part of it about the super civilization. And then if you're interested in, you definitely can watch the entire video.
There's more. The Milky Way is about 13 billion years old. In the beginning, it would not have been a good place for life because things exploded a lot. But after 1 to 2 billion years, the first habitable planets were born. Earth is only 4 billion years old, so there have probably been trillions of chances for life to develop on other planets in the past. If only a single one of them had developed into a space-traveling super civilization, we would have noticed by now. What would such a civilization look like? There are 3 categories. A Type 1 civilization would be able to access the whole energy available on its planet. In case you're wondering, we're currently around 0.73 on the scale, and we should reach Type 1 sometime in the next couple of hundred years. Type 2 would be a civilization capable of harnessing all of the energy of its home star. This would require some serious science fiction, but it is doable in principle. Concepts like the Dyson sphere, a giant complex surrounding the Sun, would be conceivable. Type 3 is a civilization that basically controls its whole galaxy and its energy. An alien race this advanced would probably be godlike to us. But why should we be able to see such an alien civilization in the first place? If we were to build generation spaceships that could sustain a population for around 1,000 years, we could colonize the whole galaxy in 2 million years. Sounds like a long time, but remember, the Milky Way is huge. So if it takes a couple of million years to colonize the entire galaxy, and there are possibly millions, if not billions of planets that sustain life in the Milky Way, and these other life forms have had considerably more time than we've had, then where are all the aliens? This is the Fermi paradox, and nobody has an answer to it.
So if you look at the video, the Earth is not yet the Type 1 civilization, so there is a long way to go in terms of our technology. Now let's move to our focus to astrobiology. So what is astrobiology? It is a study of life in the universe, of course includes its origin on the Earth. So astrobiology actually brings together astronomers, planetary scientists, chemists, geologists, and biologists to work on the same problem from their different perspectives. If we look at first the origin of life on the Earth, what are the requirements for life? If you look around, you know we need water. And of course, we need certain elemental raw material, and we need energy, as well as the environment to make the chemistry to happen to generate a more complex organic molecule, while the environment in which the complex chemistry or complex organic molecule of life is stable. Without a stable environment, or the molecule, the complicated molecule, and they will break down before they can do their job. So we need to have an environment that their interaction are also possible, so then take their function in the life. While there is no unambiguous evidence for life that we have found beyond the Earth, but when we're looking at the life chemical building blocks, like some carbon-based molecule, they actually were able to detect them in a wide range of extraterrestrial environment. For example, we already talked about there are a lot of organic molecules can be found on meteorites, the comets, and even use spectroscopy. When we look at the giant cloud of gas and the dust between stars, we also discover some of the simple form of organic molecule. So you can see the universe does not lack the elemental raw material, the building block for life. Of course, the universe does not lack of energy. There are stars almost everywhere in the universe. So the essential for us to find a place that's suitable life, that's gonna be, we want to find a place have liquid water and which have a stable environment. However, there is no way we can take a time machine, travel back a few billion years ago to look at how those organic molecules were created. So therefore, there is a very famous experiment called Miller-Urey experiment. And it's basically in the lab, they want to mimic the environment in the early Earth to have liquid water. The input of energy and a certain elemental raw material to see if they're under those conditions, if they can produce more complex organic molecule like building blocks for life, such as nucleic acid and amino acid. Let's take a look at this experiment in more detail. This is basically create a water cycle, and the bottom, they call this lower chamber. They actually have water here, and the external source actually boiling the water, so we have water vapor to evaporate and go through the tube to what we call the upper chamber, which represents the atmosphere of the early Earth. So in addition to water vapor, scientists also put some simple molecule like carbon or base like hydrogen gas, ammonia, and methane. You can see we can find a lot of them in the outer solar system where temperature is cold, right? And also input some energy resource such as the spark to mimic the lightning in the early environment or the atmosphere of the Earth. Then after the chemical interaction, the solution of water, basically with the water and the product of interaction will go through the condenser and will be all the way go down to the collecting trap. And we're looking for if with a simple input of the raw material as well as the liquid water as well as the energy input, if we can get the production of more complex organic molecule. And the result is that in the collection trap, they were able to find a complex organic molecule such as amino acid and nucleic acid. So at least we kind of know that it's the starting, not yet starting of life, but that is on the early Earth environment. That is how this complex building block of life, large organic molecule, was created. And if we go back to look at the history of life, the life appear to have spread around our planet after 4 million years after the end of a heavy bombardment period. If you trace back, the oldest life form on the Earth can trace back to about 3.8 billion years ago. However, the very important step, how the complex organic molecule and turn into life, is not yet completely understood. So this is a very complex. So far, we do not have experiment that kind of link those organic molecule to create a life. Even a simple molecule like our DNA, the gene, actually contains a million of the molecule units, and each actually arranged in a precise sequence. So even the most primitive life, such as bacteria, they actually require two special capabilities. One is a way to extract energy from environment, and also a way of encoding and replicating information in order to make a faithful copy of itself. Even the individual life die, but the format of life can last for a very long time. So life actually evolved to use many types of energy resources. For example, the plant life, the photosynthesis, they use their energy in terms of light. And the photosynthesis is a very, very big step in the evolution of life on the surface of the Earth. Photosynthesis is a very complex sequence of a chemical reaction that the living things like plants or some bacteria, photosynthesis bacteria, use sunlight to manufacture the product to store energy, such as carbohydrate. At the same time, release oxygen as one byproduct. And oxygen is actually very, very important for later on the appearance of animal life on the surface, on the land. And we actually found the photosynthetic bacteria actually in rocks almost 3.5 billion years old from those fossils. And as the free oxygen and began to accumulate in our atmosphere, which is about 2.4 billion years ago, the interaction of the sunlight with oxygen can produce ozone. If you still remember that ozone is a very important protection layer that protects us from high energetic radiation like X-ray and gamma ray and ultraviolet from the space. So therefore, this provides a chance that allow life to actually move out of the ocean and start to colonize on the land. And also oxygen is also a very essential gas for the animal because animal inhale oxygen but exhale carbon dioxide. And so that's pretty much the evolution of life on the earth. But if we look at the format of life on the earth is not just human being. We actually have very diverse life on the earth. And there are some life actually are living in what we call a very extreme condition. If you think about our body only works with a very narrow range of the temperature of a body temperature. So that's why we actually need to put on warm clothes in the cold climate. Also only work on our very narrow, what we call the blood pH value. And beyond the limits, we're basically in a serious danger. So for example, if the body temperature gets too hot, they can cause molecule not stable. If it's too cold, it will basically slow down the metabolism to a very low level. However, if you look around Earth, there are actually a lot of organisms, especially like bacteria, microbials. They can tolerate the very extreme condition. Just give you some examples. This is a very famous Grand Prismatic Spring in Yellowstone National Park. You can see the center hot spring, the temperature is about 19 Celsius, is near the boiling point of water. You can see this is actually have very colorful surrounding of green, yellow, and orange color are actually all from the bacteria microbials that are actually able to live in this condition. And if we look at other examples of this, what they call this on the ocean hydrothermal vent on the seafloor. The hydrothermal vent basically there is some like geothermal come from. The temperature is also extremely high, as well as the pressure is extremely high on the seafloor. And we can also find a lot of like heat tolerant microorganisms actually around this hydrothermal vent. And this black smoke actually is a superheated water filled with a mineral of metal and sulfide. So those can be like raw material for the life. And other examples is that if you look at this image is a very acid river in Spain. And the pH is very close to 2. So it's basically literally a river of acid. But we found, you can see the color is like a reddish. We actually found acid-loving microorganisms not only thrive in this water, but their actual metabolism activity help generate the acid in the first place. So this red color actually coming from those microbials. And the last picture you can see here, there's a pink and a reddish color here. This is actually from the salt pond. So the water of this salt work, the water of the evaporated salt work near San Francisco And the color pink is actually coming from the community of photosynthetic organisms. And this water about 10 times as salty as seawater. So you can see some organism can even survive and thrive in these conditions. Because of this proliferation of life into these so many extreme environmental conditions, actually make us so optimistic about the chance the life could exist elsewhere, even if the planet do not have the exactly condition as Earth. Maybe it's too hot, or too salty, or too acid, or even too cold. Maybe some form of life, not really human being, but other type of life may still survive at that location, which can explain the candidate place that we are actually able to find the existence of life. Now let's talk about our journey searching for life beyond the Earth. So let's begin with the searching for life in our own solar system. If you look at the most close candidate is actually Mars. Mars appeared to have been a more similar environment compared to Earth during its early history. From the result of the handful of roller and orbiter and lander on Mars, we actually found used to be a lot of water on Mars. Although the surface of Mars is so far is lifeless, but next step we want to dig into space underneath the surface to see if we can find some evidence even for the past of life on Mars. And if you remember when we talk about the moons, and Europa and Enceladus are the two moons. They likely host a vast sub-ice ocean because Europa, we see the surface is constantly renewed by the liquid water which from the underneath, and we suspect there is our ocean underneath the surface. For Enceladus, in this picture, we see the salty water geyser actually coming from the underneath the surface. So those two is also a special interest for us. So if we will send future mission to see if we can find evidence for life in its sub-ice or underneath oceans, because we believe the liquid water, remember, the liquid water is essential element for the life to begin. And we know in the space is no lack of raw material and energy. And we know that the underneath ocean may providing the habitable condition. And on the other hand, Saturn's moon Titan that is also very interesting. Although there is no liquid water, but they have liquid methane, and they have thick atmosphere, although it's made primarily from nitrogen, but they might be an environment we can search for a different type of a life. Maybe it's not liquid water based, but liquid methane based type of a life. There are a lot of organic chemical reaction happens to generate a lot of chemistries. So maybe then that means they actually have abundant raw material building block for life. So definitely in future we'll send mission to Titan to look for more detail to see if there's a different form of life we can find on the moon of Titan. In order to expand our vision, we start to looking at the exoplanets. And first in our own Milky Way galaxy. And with advance of technology from previous chapter we already talked about, so far we already identified more than 5,000 exoplanets, and among them there are Earth-like exoplanets. And because there's millions of stars in the Milky Way galaxy, and a lot of stars actually have a couple of planets orbiting around them, that even the percentage of life on planets is very, very, very low. With a large number, that's also lead us to believe that there may be a chance we can find life on one of the exoplanets. And also because we have billions of stars, and turns out even more than billions of actual planets, there must be some of exoplanets with similar as the Earth, and it's also habitable for life. And so this is the artist's illustration of Earth-like exoplanets, and we actually can identify so far. And of course, other than the similar terrestrial surface and similar size as the Earth, we want to search for life on those actual planets. They are actually, we call it in a habitable zone. So a habitable zone is a region around a star. It's not too far, not too close, where the suitable condition might exist for life. So we're looking primarily for in which condition the water could be present in liquid form on the surface. For example, if you look at the habitable zone on the solar system, we're pretty much like the Earth, the outer planets, they are just too far from the sun. So basically that they won't get enough energy to maintain their temperature on the surface. Of course, those outer solar systems, some of the moons, they may have geothermal energy that can provide energy resource. But in terms of their location in the solar system, they are not really a possibility that the water, liquid water, can be survive on their surface. And the habitable zone also depends on other factors, such as the level of greenhouse effects. For example, if you look at the Earth, Mars, and Venus, we actually all pretty much at the similar distance from the sun. But the greenhouse effects on the Earth is perfect level. So basically raise the surface temperature about 33 degrees. However, if you look at the greenhouse effects on Venus, it's too much. It raises the temperature over 500 degrees Celsius. So basically, if there's too much greenhouse effect, the liquid water cannot survive. On the other hand, if you look at the Mars, there's too less greenhouse effect. So therefore, Mars is too cold for liquid water to be stable on the surface. And other than that, it also depends on the luminosity of a star. So you can see if the star is much brighter than the sun, of course, we'll move a little bit further away from the star. Otherwise, it will be too hot. If the star of actual planets orbiting around is less luminous than our sun, so you are looking in a region that is closer to the star. You can see there's a lot of factor play. The planet is actually in a habitable zone, and not only the distance. So far, the scientists are working to understand all the factors that define the habitable zone and the habitability of the planet. Because there are so many exoplanets, this will be our primary guide in targeting some exoplanets on which to search the evidence of life. Even the planet is habitable, it is not necessary there's a life on the planet. The next step is definitely get some information from the planet to see if there's indirect evidence of life. One problem is that even the closest star is about 4 light years away from us. The travel directly into those exoplanets is almost impossible. So therefore, the study will be focused on if we can analyze the light from the exoplanet or other kind of radiation. We can, to see if we can search for some biomarkers indicates the presence of life, and such as photosynthetic biosphere on the Earth. Just take Earth as example. We know Earth is covered by a large area of ocean and plants. So therefore, when we look at the Earth from space, Earth look bluish and greenish due to the ocean and the plants. So that means when we reflect light from the Earth, and a lot of light will basically absorbed by some molecule actually produced by the life on the Earth. For example, in the atmosphere of Earth, we know there's a lot of oxygen and ozone. And if we look at the percentage of atmospheric transmission or absorption in the entire spectrum, especially if we focus on UV, visible, and infrared radiation, we can see there's a lot of absorption downwards peaks. So especially here in UV, absorbed a lot by oxygen and ozone. So remember, oxygen and ozone on the surface of the Earth is a byproduct of life. And therefore, you can treat as oxygen as what we call the biomarkers. And of course, there's other kind of gas in the atmosphere. We can identify that's a byproduct of life. Then also can indicate it might be the life actually produce all these molecules. So for example, if extraterrestrial intelligence want to detect the Earth, of course, when we view us in the visible spectrum, the Earth is pure blue and green. So definitely it's very different from other lifeless planets like Mercury or the Moon. Then they only have like a grayish rocky color from a rocky material. And also the absorption of the atmosphere of the Earth or the chemical composition of atmosphere of the Earth is definitely different from the atmosphere of other planets, lifeless planets. For example, on the Mars and the Venus, we know they only have carbon dioxide. On Titan, the Moon, they only have nitrogen, but the lack of oxygen. So those all can act as a biomarker for us to narrow down the actual planets they may have life. But again, before we determine if it is a life actually produce those biomarker, we have to first exclude other chemical reaction can still produce those biomarkers. So you cannot simply see there's oxygen in the atmosphere, you see, oh, there's a life. That is not. We need to look at all the possibilities and rule out other possibilities so that make only the life can produce such a biomarker before and confirm that is a life on an exoplanet. Just give you an example like Mars, before we actually send spacecraft, lander rovers to take a close look at Mars, we can see there's a dust storm on the Mars. It looks like the seasons of the plants grow and die. We even see the Valles Marineris. We thought that is a canal built by the Martian. But turns out they are actually not associated with life. The change of the surface, the darkness of the surface of Mars is due to the dust storm, not plants. The valleys is actually just from the plate tectonics. And even search for those biomarkers is not that easy. And remember, if we look at the Earth and those biosignatures in the atmosphere like oxygen and ozone that we have today, although could supply good evidence for the life, however, we do not have them for our early history of Earth. Remember we mentioned the oxygen, for example, only accumulates to detectable level in our atmosphere only a little over 2 billion years ago. So that means if the life is in the early stage on an exoplanet, we still may not able to find any evidence of the biomarkers. Or that the life on the planets is already disappeared, that will also change the environment a lot. We may not able to find those biomarkers. So although biomarker can give us good hint of which exoplanet actually may have life, but for some cases we may not be able to detect biosurface or biomarkers even if the life exists. Now I want to share with you a video about a habitable zone from NASA.
We inhabit a little blue planet called Earth. Earth is habitable because it had the right conditions and ingredients to enable life as we know it to evolve and flourish. And one of the most important factors in making our blue planet habitable is the wet stuff itself, water. It's kind of extremely important for life. When it comes to the search for habitable exoplanets, planets outside our solar system, we think the ability to have liquid water on a planet's surface is just as important for those worlds. There's a handy concept astronomers use to help them figure out where to look around any given star for exoplanets that just might have the right stuff for life. It's called the habitable zone. It's the distance from a star where a rocky planet with an atmosphere could have liquid water on its surface. In our solar system, the habitable zone extends from around the orbit of Venus to around the orbit of Mars. Earth happens to be nice and comfy in the middle, but it takes more than just a good location. Orbiting in the habitable zone does not guarantee a planet will be habitable. After all, the moon is right here with us, but it's certainly not habitable. Sorry, moon. The location of the habitable zone depends on how big and bright a star is. The nearest star to our sun, Proxima Centauri, has at least one planet in the habitable zone. But because Proxima is much smaller and dimmer than our sun, its habitable zone is way smaller and closer to the star. So every star has a habitable zone, but that doesn't mean there will be planets there. For example, the star known as Kepler-90 is similar to our sun, and it too has 8 planets. But they're all huddled super close to the star, well inside of the habitable zone. But the longer we look, the more likely it becomes that one day we'll find another little blue, water-covered planet right in its own comfy habitable zone. And that would be a planet worth a closer look indeed.
And of course, if you're interested in and our searching for life on exoplanets, I definitely refer to you to the NASA website, Exoplanet Exploration, so you can read more about the news, how many Earth-like exoplanets we already discovered. They're adding new information about what type of planet they are. And finally, in this chapter, let's talk about the search for extraterrestrial intelligence. So basically search for an intelligent life, such as human or even advanced in technology than human being. So sometimes we refer that as SETI, search for extraterrestrial intelligent life. Other than human being, so far we didn't really not found any intelligent life within the solar system, and for all the planets and the moons we already explored. So far we only try to looking for like the basic format of life, like microorganisms. And therefore, for the intelligent life, we will need to go beyond our solar system. One way is definitely to travel to those stars. But if you think about the travel directly, it is a very, very slow based on our current technology, and it is extremely expensive. Even we talk about the nearest stars, based on the speed of spacecraft that we have for human species to travel there, it will take about 18,000 years even to get the nearest star. And the energy we're going to use, even we assume we're going to use a perfect machine with a 100% efficiency, the total energy that we need to travel to the nearest star equivalent to several 100,000 years of worth of total energy used in US. Therefore, it's just too slow and extremely expensive. Based on our current technology level and situation, we can afford any of interstellar travel. I know you may heard about there's a lot of UFO report, but so far there's no evidence that any UFO report are related to extraterrestrial visits. You can think about it in another way. If the life is similar as Earth in actual planet orbiting around another star, similarly compared to Earth, their technology may not that advanced. They still don't in a good shape or in good condition. They want to spend so much energy or travel for tens of thousands of years to reach the Earth. Although it is not possible for now for human beings to travel interstellar, but the robot probes such as spacecraft, they can carry messages. They can travel over a long distance and a long time. And so far, there's 5 spacecraft, 2 Pioneers and 2 Voyagers and a New Horizon. They are now leaving the solar system. So on board the Pioneer spacecraft, they actually have a plaque with a picture message engraved, appearance of male and female, and as well as our location in the solar system and where the spacecraft come from. You can see this is about like a simple drawing. Even the aliens without knowing the language on the Earth, they can somehow understand what it's talking about. And the Voyager's spacecraft have audio and video records attached, which allows the inclusion of over 100 photos and a selection of music from around the world. And hopefully one day the extraterrestrial intelligent life can kind of retrieve those information we send with the spacecraft, and they know we actually exist on the surface of the Earth. And some updates about those 5 spacecraft. And so far, the 2 Voyagers, we still have communication with them. They are actually already kind of in the outer edge of the solar system. So they are already outside what we call the heliosphere. So that they already in the interstellar space, the space between the stars. And the Voyager 1 actually made it to the interstellar space in August 2012. And the Voyager 2 entered the interstellar space on 2018. So now the New Horizon, which after its visit Pluto and the Kuiper Belt, will join the Voyagers and is also heading towards the interstellar space. Unfortunately, although the Pioneer 10 and Pioneer 11, the two Pioneer spacecraft, both stopped functioning, but they're still we know they are still coasting into the interstellar space as a ghost ship. Although we cannot communicate with two Pioneers, but they are still heading towards interstellar space, and hopefully the extraterrestrial intelligent life can find them one day. And the Pioneer 11 is traveling towards the center of the Milky Way galaxy in the direction of Sagittarius, and the Pioneer 10 is actually traveled towards the constellation Taurus. Of course, if you want to know more detail about those missions, I definitely suggest you to visit NASA website. For example, the Voyager 2, which is the most successful mission of NASA, is not only visited all four outer planets. So far, the only flyby of Neptune and Uranus is by Voyager 2. You can see the mission is already lasts for more than 5 years. And this is basically a simulation, give you an idea where is a Voyager 2 right now. So you can see it is going into the interstellar space since 2018. And unfortunately, we are still able to communicate with Voyager 2. If you look at the K dates, in August 2023, we actually resumed the communication with the Voyager 2, although it takes a very long time for the signal to send back and forth between the Earth and the spacecraft. And other than the space interstellar travel by the spacecraft, our easier way to communicate with extraterrestrial intelligence is by exchange messages and with electromagnetic radiation. For example, you can see we even can see the light from galaxy 1,000 light years away from us. So of course, the light can bring a lot of information and travel over a very long time, over a long distance, and reach at another place in the universe. And among all the electromagnetic waves, the best option going to be radio wave. You may still remember that the radio wave can go around the clouds, can penetrate the dust clouds, the interstellar gas, and dust. So therefore, the radio wave will not be blocked by most of the objects. So that makes us the best option for us to communicate. So even when we communicate with a satellite or spacecraft, we primarily use a radio wave. If there's any communication message sent by extraterrestrial intelligence, and what we should looking for, there is a lot of questions. Which star we should focus on? What kind of frequencies of a radio wave they will send in the message? What type of signals they will use? And there's other factors. So we call all these questions like cosmic haystack problems. This is just assuming that we are only trying to receive messages sent by extraterrestrial intelligence, not yet how we send message to the vast universe. Even we have radio telescope to receive those radio signals from the extraterrestrial intelligence. From which direction is the message come from? On which frequency is the message being broadcasting? How strong is the signal? How sensitive should our radio telescope be in order to detect those type of signals? And how is the message encoded in the signal? And definitely they probably won't send a signal in English or any language developed on the Earth. Even we receive the signal, how we decode the signal to get the information. And how can we recognize a message actually from a complete alien species? You can see there's a lot of questions to ask. And fortunately, with advancement of technology, we can build more and more powerful radio telescopes to search for extraterrestrial intelligence. So therefore, some question will be solved. We can just cover the entire spectrum of a radio wave, so we don't really need to identify which frequency of radio wave we're looking for the message. In recent years, the engineer on the Earth actually figured out that we can actually send a very brief, bright pulse of visible light, then can be detected from a distance away. If we follow this logic, that means the extraterrestrial intelligent life may also able to do that. So other than searching for the radio signal, we can also search for this brief, bright pulse of visible light. And also, if there's a huge construction project by advanced civilization, such as renovate their planetary system to maximize the area for life, those big renovations could do so by breaking apart some planets or moons, or build rings of solid material that surround the stars. And such a big construction project will definitely emit some of the infrared radiation, or we can looking for the infrared signature of this huge construction project by the advanced civilization. So you can see we have this what we call wide field infrared survey explorer is a space-based infrared telescope to looking for some infrared signals that signature the huge construction. And lastly, there's also a big questions. If all the extraterrestrial intelligence are all just try to listen to the information sent to them, and nobody actually sent out any information like us so far, then of course there's no way we can receive any of the information. And the big question is that should we transmit information in addition to just listening? And if we do decide we want to transmit some information, and who decide what to include in this information broadcasting into the universe by the Earth, as well as if we do find a signal someday from extraterrestrial intelligence, should we answer, and how do we answer? And those are a lot of questions we need to determine, and before we either receive the signal from extraterrestrial intelligence, or we want to transmit or send signal to broadcast the existence of human being on the Earth to the universe. Some concern from the scientists is that they warn that our civilization may be too immature and we are defenseless to announce ourselves at this early point in our development. So it's very interesting reflection of how we feel about ourselves in our place in the universe. And in terms of the status is that of the searching for extraterrestrial intelligent life, so far we did not get any evidence. We'll continue to searching for extraterrestrial intelligent life using the radio telescope and the radio arrays, as well as other tools we have. At the same time, while we are waiting, we also want to take time to think about what happens after, in case we receive the signal from the aliens. That is all I want to talk about in Chapter 13, Life in the Universe. First, we talk about the cosmic context of life. Then we talk about astrobiology, how the life was developed on the Earth. And after that, we're talking about searching for life beyond the Earth. We start with the solar system, and we did not really get a very promising result. Then we extend our search to exoplanet orbiting around the other stars. And we talk about what kind of target we're looking for, what kind of evidence we're looking for the evidence of life exists in exoplanet. And finally, we talk about searching for extraterrestrial intelligence, what effort we actually made so far, such as send spacecraft into the interstellar space and build a radio telescope to receive the signals from extraterrestrial intelligent life.